Welcome, everyone. Chris is going to be telling us about Joule's algebras and related structures. Take it away, Chris.
Thank you very much. Thank you for the kind introduction and the opportunity to give a talk. Yeah, indeed. So Joule's algebras and related structures is a little vague. When I was asked to give the talk, there was sort of a polite request that it be something approachable, maybe for grad students and above working in the VOA space. And so what I wanted to kind of do was give a talk that's more or less split into two parts, right? So the first part, I want to describe what I'll broadly refer to as the physics approach to Joule's algebras, right? This is the ephemeral zero modes acting on the top space algebra. And in order to do this, and there's a number of great references, I'll roughly follow some path that weaves its way through the following four texts, right? So there's a very nice introduction to conformal field theory given by Matthias Gabadil. There's a nice paper by David and Simon Wood, which is on something completely unrelated, but an appendix has a very nice write-up on sort of the two ways of thinking about Joule's algebras, in that this physics approach and Joule's original approach. There's, of course, the Bombay Lectures book by Katz, Rayner, and Roshkovskaya, where they discuss at least aspects of this in lecture 18 from a little more mathy perspective. And there's all of the essential results basically encapsulated in Joule's 96 paper. Now, after that, so sort of this nice historical review of hopefully something interesting, I want to talk a little bit more about Joule's algebras and where they're appearing now in sort of the modern research space. And this will be slightly more maybe of an advertisement than anything else. This sort of try to link together some new ideas and advertise some new research pathways that we can hopefully explore. So these are things, what I want to hope to get to, things that I haven't studied extensively. I mean, it's really only been a couple of months, but I think there's some very interesting things to do in this space. And if anyone's more of an expert on the types of things that I'm talking about than I am, then let's have a chat, because I think there's plenty of room to do some good work. All right, so let me get started. We'll start right at the beginning. So what I want to do is I want to start with the setup. I want to start, of course, with a vertex operator algebra. And I want to put to begin with, quite a few niceness properties on that VOA, right? So I want to assume that V is n graded, right? Non-negative integer graded, and that it's finitely strongly generated, right? So what do I mean by that? So I have some set of vectors that live inside my VOA such that the fields corresponding to those vectors, right? So here I have my usual field map. The fields, their derivatives, and the normally ordered products of the fields and the derivatives can be used to describe all the fields that act on V, right? Up to linearity. And take linear combinations of these things gives you everything. Right? So these are, in a sense, kind of like the nicest set of VOAs that we can start off with. And really, like the motivation behind this is because I want VOAs whose mode algebra has some nice PBW basis, right? That's kind of where we're going. These things are the things that you sort of see appearing in physics. Okay, now we are talking about Joule's algebras. These things are connected at least in some way to modules. So let me introduce a V module, right? So let's say I have some V module, I'll call it M. Now I want this thing also to be graded. I don't want this to split up into weight spaces. Here, let's just take H to be some complex number. And then so each of these spaces here might be generalized eigenspaces for L0. This is sort of the formalism to which we can extend this. But the discussion that I want to give here is pretty broad strokes, just like a motivation for this other viewpoint of things. So taking R equals 1 in your head throughout this whole thing will be fine. And I think I probably do it a bunch in the things that I write and the calculations that I do. Right, so I have some V module. It's some vector space that's going to have some action of my VOA on it. We'll talk about that action on the next slide, but something I want to distinguish just quickly, right? I want to introduce this idea of what's called the top space. This is something we're going to use often. This is what we'll call like the space of ground states, right? So this is, if you think about having some bounded module, some cutoff on the eigenvalues of L0, this will be the top space if I draw going down the page what my modules might look like in weight space, right? So here we can quickly throw in some examples. Let's say for Virasoro, I have some highest weight module. I take some generating vector, let's call it V. Oh, nope, let's not do that. I want to go this way, right? So I have some generating vector, let's call it V. And then I might have L minus 1 acting on V sitting beneath that, and I have L minus 2V and L minus 1 squared V sitting beneath that, and so on, filling out my module. Then in this case, this space up here will be my top space. Now I can think about something slightly more interesting. I can think about modules over affine SL2. In that case, what's a very nice example is something like the usual finite top space, the admissible highest weight modules, right? So here I might have some series of vectors at the top where this will be my V. This would be like F0 acting on V. This would be F0 acting twice on V. And maybe that's sort of the profile of my module. Here I have some state down here given by E minus 1 acting on V, and so on. And in some example like this, my top space would be this space of vectors just here. Right, so this is something that we're going to at least think about in the back of our minds. It's nice to have some pictorial examples of what we mean by this top space. Okay, so we have a module. Part of having a module means we have some new field map, right? So there's some field map that acts on M. It takes a vector and an argument. It produces now some formal series, but now all of the coefficients in my formal series are endomorphisms of my module instead of endomorphisms of my vertex algebra. Now this upper lower M notation ends up getting really clunky. I think everywhere from now on, there's just going to be M's all over the place. And so what I'll just do is we'll just remember that there's M's everywhere and we'll leave it off. And it'll be a little bit easier for us to follow, at least I hope. Okay, now because of the grading on V, right, M top is going to be a space that's annihilated by all of these modes that I have, right? Implicitly here, I'm thinking of this maybe having an M floating around. So this space is going to be annihilated now by all of my modes where this index is strictly greater than 0. Right? This is just a natural consequence of the grading that I have. Indeed, I can go a little bit further. I know that if M is simple, right, if it doesn't have any singular vectors, because singular vectors should also satisfy some criteria like this, then M top is exactly the space of vectors in M that vanishes underneath this particular action. All right. Now, from a physics perspective, what do we want to do? Well, we want to compute amplitudes, right? So there should be some state in my theory that's generated by some primary field. This thing corresponds to a module. And what you want to do is take amplitudes, right, which is in principle sandwiching your module and a bunch of fields inside some nice inner product like this, right? So let's assume that I have some simple module M and I have its dual M star, right? I can write any state as some descendant of M top, right? I can work my way down using the modes. And so what I really mean by when I say amplitude is some sort of inner product like this, right? So here I have some dual vector. I take the inner product with some product of fields. And really from a physicist perspective, what you're doing is you're getting some space-time dependent way of measuring the probability, or at least something that will square to a probability of transitioning from this state here to this state here through each of these types of actions, right? So this is something you want to calculate. Fundamentally, from a physical perspective, this is kind of exactly what you want to calculate. And in a very broad stroke sense, this is almost everything you want to calculate, right? So this is what you'd call transition amplitudes within a particular sector. Once you know this, and then how to transition between sectors, which would be your Pointing operators, you in principle have figured out everything, modulo some details. So this is sort of the natural first step. Okay, now what can I do with some sort of expression like this? That's going to be our next step. So I can start out by doing something very naive, right? I can start out by expanding all of my fields as formal series, right? This lets me write something like I take my amplitude and I write some sum over here. Now, in principle, this is some big, horrible multi-sum, right? This is a mess. And what I can do is I can write some expression here that's just in terms of modes. And then over here, I have some analytic function, right? And it's a mess of an analytic function. It's going to have all of these z's in it to all of these funky powers, but in principle, it's just some analytic function. This part here is going to be the part that I worry about for the next little bit. Okay, so the axioms of having M be a V module enforce a couple of things, right? The first thing that it gives us is that my amplitude has to transform appropriately under Möbius transformations, right? So these things are supposed to describe conformal field theories. These are exactly my conformal symmetry transformations. My physics should be in some sense invariant under these transformations, right? That's part of my game. The other thing that I have as part of being a V module is that it needs to respect the OPE, right? So if I have inside my amplitude somewhere the product of two fields, well, I need to be able to, purely because of how my VOA works, I need to be able to substitute in for this product some notion of the OPE, right? I need to have some compatibility with the product structure in my VOA. So here I've got my OPE. It tells me that if I multiply YA of Z and YB of W, then I get some series which has some set of singular terms appearing in it, right? I get some sort of expression like this. Okay, so here we've started deconstructing the amplitude. We have some constraints that are very natural. How can we use this now to make some forward progress on this whole thing? Okay, so the first point, this Möbius invariance tells us a few different things, right? At a VOA level, these types of VOAs that I'm thinking of, it tells us that it essentially decomposes as SL2 modules. And I don't mean affine SL2, I mean the genuine SL2 that lives inside my Virasoro algebra that's generated by these three generators, right? L-1, L0, and L1 give me a copy of SL2 that act very naturally on my VOA. These are the things that are generating my Möbius symmetries, right? I'm exponentiating these to get global symmetries of my whole theory. So if I forget about this complex analytic function that's hanging on the end, what I can do is I can use the action of this SL2 to show that some expression like this, right? This is my general amplitude, just the mode part, where I have lots of little indices floating around. Well, I can finagle this, right? What I can do is up to some overall coefficient, I can write this now as just the zero modes, right? So conformal invariance tells me, well, okay, well, if I have to have this be non-trivial and this thing lives in the top space over here and this thing here also lives in the top space, then whatever expression I have inside has to respect the grading on both sides. And then it just becomes a matter of using these constraints in the SL2 action to come up with some overall constant of proportionality. Now, that's in general ugly, but in principle, it's calculable if you know what your VOA is, right? So I can finagle these general expressions into zero modes acting on the top space. All right. The second point, right, this point about the OPE tells us that there's some non-trivial algebraic structure on the zero modes that I need to have be compatible with this whole picture, right? So that's going to be like the next thing to extract. Okay, so just to recap, because at the moment we're maybe getting a little lost in the weeds, right? This idea is that we have simple lower bounded weight V modules, and they're in some sense determined, right? This is telling me, in essence, everything I want to know about my module. It's determined by the action of the zero modes acting on the top space, right? So this, you can flip this around, we can realize that, okay, well, this top space, whatever it might be, is some simple highest weight module for my zero mode algebra, right? I have some nice way of moving around in exactly this space, and I never really leave it because of compatibility conditions I have on my pairing. Now, the question is, how do we determine this algebra, right? This so-called algebra of zero modes acting on the top space. How do we actually extract this information? Now, there's many different ways of doing this next part. I'm giving you the flavor that I find most compatible with how my brain works. Other people have other ways of explaining this, and they're all realized in that collection of references that I gave you at the beginning. So if we go through this argument and you're like, man, where the hell did any of this come from? Or like, what is going on? That's fine. Either come to me, we can have a chat, or have a look in those references. I'm more than willing to have a chat. But this is the one that works well for me. So what we can do is we can take the Borchards relations that we have on V, and we can produce, right? We can go in looking for trying to produce zero modes, right? So I might have some expression like this. This is some general expression that I can extract from the Borchards relations. And the important part is, okay, I write some mess over here But really what I'm looking for is I'm trying to understand the zero modes of things that come out of the OPE, right? Something like this would be the zero mode of something that's coming out of my OPE. There's a very intentional link between the expression here inside the zero mode and the expression that's inside my OPE field. Now, this is some expression that holds generally in V. The right-hand side is not strictly zero modes, right? There are modes of all kinds of indices appearing in this expression. Let's try and make life a little bit easier. Let's start by applying this type of expression, right, to some vector that lives in my top space. Now, when I do that, okay, well, I do that to both sides. Now I take this big ugly expression that I have here, and I recall that if M lives in my top space, then I know that any of my positive modes, right, any one of these endomorphisms that has an index underneath here that's a strictly positive integer is going to annihilate that vector. So this massively truncates this huge sum down to just this thing here that comes from this term when j equals 0, right? This term here is going to contribute 0 for every single one of my j's, and just one of these will survive. Now, on the right-hand side of my expression, what I have is something like this. And this is not something I can simplify, but that's okay. It turns out this is enough. This is essentially what we want, right? So I can take this expression that I have here. Oh, I wanted a pen. There we go. I can take this expression that we have here, and I can make M implicit, right? So these two ideas here are linked. And we get that I should have some sort of product on my zero mode algebra that looks like this thing here. This is kind of the golden nugget. This is what we were chasing all along. This is the product structure on my zero mode algebra, right? Inbuilt into this is the fact that I'm acting on vectors in my top space, right? There is part of this whole game is that I have implicitly got this thing here, this M floating around internally. Okay, so now that we have this product structure that we've extracted, this leads us to what I'm going to call the alternative definition of the Joux algebra. Right, so this takes a little bit of setup. Now, suppose V is a VOA as we had above, right? So this is, I haven't really changed too many of the adjectives that we'd associated with our VOA, right? I still want some nice VOA, n-graded, and finitely strongly generated. Now, what we get with that, we get some enveloping algebra of modes, right? Some nice unital associative algebra that I can write out like this, right? So I can call that thing U, and I have some nice decomposition, which is essentially my PPW theorem that's telling me, okay, here I have the ANs where n is less than 0. Here I have the ANs where n equals 0. And here I have the ANs where n is greater than 0. All right, now I need to just introduce a little bit of notation. Let me call this thing here, you might think of this as like the derived part of this unital associative subalgebra. Each of these are those. Maybe it's helpful if I draw multiple arrows. All of these things are unital associative subalgebras. What I want to do here is I want to split off sort of the one, and I want to introduce notation here for just parts that live in an actual AN with some n greater than 0. Right, so here I want to take some subalgebra, like the ideal inside that subalgebra, which is only represented by the modes. Okay, then this is where we get to the definition. The Joux algebra of V is a unital associative algebra that's given by the following thing, right? So as a vector space, we want to take this algebra of zero modes, and then we want to quotient out of this thing some funky looking quotient. And what we want to do is we want to put a product on here, which is the product that we had on the previous slide, right? It's just that if I take the product of two of my zero modes, which are things that live in this space, then I want to have this right-hand side. And really, I haven't done anything to that right-hand side because the structure of this right-hand side is going to be V dependent, right? It's going to matter a little bit what type of vertex algebra I have. Right, this funky bracket notation, this is just indicating, right, when we write something like this, that what I'm doing is I'm taking the image of A0, which lives in this zero mode part, in the quotient, right? So in this particular quotient that's given, I want to take the image of any one of these, and I want to do that for every vector that I have in my vertex algebra. Okay, so this is sort of the definition that comes from the physicist's approach to this whole game, and that gives you something that's equivalent, right? You might have two questions. I certainly had two questions the first time I saw such a construction. The first one is, what on earth is this quotient doing? That turns out to be kind of nice, and we can extract that shortly. The second one is, how does this relate to Jou's definition? And that's a little bit trickier. Oh, sorry, I see there's a question in the chat. Oh, maybe not. Okay, no worries. Sorry, I had a little one. Feel free to ask questions, by the way, if anyone has any. All right, so the first question is, what on earth is this quotient? The second question is, how do I relate this explanation that I've just given you back to Jou's original definition? All right, so let's start with the first question, right? So the zero mode of some normally ordered product, right? This is in essence like the nicest possible example. If I have the mode an, right, where n is minus the conformal weight of whatever a is, I act that on the vector b, and I take the corresponding zero mode of that field, which is what this notation is trying to say, right? It's equivalent to writing something out like this. Well, this is some expansion that I can write out. This is just using an a definition of a normally ordered product. Now, we can make this a little bit more concrete. Maybe we try to do that. Let me just zoom out a little bit. There we go. Let's take some really nice example. Let's say T is, for example, a Virasoro field, and A is, for example, a Heisenberg field, right? So I want to try and evaluate some nice expression like this. Well, then I have some very concrete sum. I can write this whole thing out. I have ln A minus n. I have A minus n ln. I have some splitting point that depends on the conformal weight of my left vector. And what I want to do is I want to think about what this thing would do if it were to act on a top space vector, right? So if I was to act such a thing, right? So come along and implicitly over here act both sides some m in m top, then what's going to happen, right? Well, then all of the terms that I have, for example, here, right? Here I'm going to have, that's not what I wanted. There we go. In this term here, I'm going to have a minus n, which is going to be some a sub a positive integer acting on m. All of these terms here are going to disappear. And over here, I'm going to have something that I need to be a little bit more careful with, right? So here I'm going to have a term with L minus 1, which is appearing here. And here I'm going to have also appearing the term where I have both zero modes acting. Right. So what this quotient is really trying to do, what this quotient is exactly doing, is it's taking some expression like this, and it's getting rid of exactly all of these terms where on the right-hand side, I have something that has a strictly positive mode index, right? Because I know when I act such an expression onto a vector that lives in my top space, these expressions have to vanish. So that's what I'm quotienting out by. What I'm left with, right? What I'm left with after this quotient are terms that look like this here, right? So in this example, these will be the two terms I'm left with after applying to n. They're also the two terms I'm left with after applying my quotient. Now, what do I do in this case? Well, here I have something that I can't do much about. I have a product of two zero modes, right? There I need some sort of relation on my zero mode algebra. Here, what I can do is I can take this expression and I can rearrange it, right? So this thing here, I can use the commutator to write such a thing as an L minus 1 A1, which vanishes, and then something proportional to A0, right? In this particular case, I'm going to get something proportional to A0 because that's just the commutation relations that I have access to, right? So we can see that this whole construction that I have is in a sense sensitive to the structure I have on V, right? I need to know things like relations, my commutators, I need to know the OPEs. But when I do have such a thing, we have a nice calculational framework. Okay, now that's sort of the first question. What on earth is this quotient? This quotient is getting rid of all of these expressions that would naturally vanish under application to the top space. The second question, it's a more detailed question, right, is how do I relate this to Jou's definition? Now, in the reference that I gave by David Ridout and Simon Wood in that appendix, that in particular gives a very nice comparison between these two pictures, right? Their description of exactly where the zero mode product comes from is slightly different. They use like a contour integration perspective. One can certainly do that. But I think in terms of relating the two pictures, they give a very nice and very detailed, very fleshed out way of realizing exactly what the details are. I should say at this point also, I mean, I make this out maybe a little bit like it's two completely separate pictures. It's worth noting that Zhu and Igor Frankl and many others at the time were very aware of this approach, right? This approach by physicists was strongly motivating the ideas that they took into trying to write something down at purely the VOA level that did these same types of operations, right? So it's not like this is totally out of left field or some, completely different way of looking at things. I mean, it's a very different formalism, but I think conceptually speaking, they're very closely tied together. And I mean, you can see this in the papers at the time that were coming out in the early 90s. I mean, people were certainly aware of this description in terms of zero modes acting on the top space. Okay, so in principle, we've answered our two questions. Now what? Right, so what is the upshot? The upshot of this formalism, right, although it requires a little bit more information, the upshot is my following claim, and my claim is that calculation is easier with the physics approach. Right, so here we can do an example, or at least we can partially do an example. I think that's useful to see. Let me take the Beshadsky-Polyakov algebra. So here I want to take k not equal to 3. It's generated by 4 fields, right? So I have my strongly finitely generated. These fields are bosonic. They satisfy these OPEs. This is mostly just here for reference. I don't want people to memorize these things. Naturally, all right, that would be rough. It's a lot to pay attention to. But I think for those of you certainly who are very aware of these types of calculations and closely following along, you'll notice that what I've done is I've chosen a version of Beshadsky-Polyakov that has integer grading on things, right? So there's 2 ways of grading this thing by L0. I've chosen the one that gives, there we go, that gives G plus conformal dimension 2 and G minus conformal dimension 1, right? They still have the same, this happens every time. Always accidentally double click. They still have the same net charge with respect to this J, this current field that I have, but this current field, right, J is now no longer a primary field. This term here is in particular non-vanishing, so I don't have J being primary like I did in the previous approach. Nevertheless, we forge ahead, so we can do some examples in this case, right? What do I want to do? Well, the important part to remember, right, there's, other than the fact that I've done this funky twisting of things, the Zhu algebra is going to be generated by these 4 elements, right? These are going to be then the zero modes of my field. So the images in this quotient are going to be what generates my Zhu algebra. What's left for me to do is determine the relations between them, right? In the same way as the universal enveloping algebra of a Lie algebra, I have some non-trivial commutation relations between these generators. Right, so that's the next thing for me to work out. Now, the first point is that L0, right, the zero mode of the Virasoro generator, this is always something that's central in this approach. There's a few different ways of seeing that. You can just go ahead and do the direct calculation. The calculation in Zhu's formalism is also particularly nice once we've identified what the quotient of Zhu's star product is, for those maybe more familiar with that picture of things. But I mean, there's a very nice way of explaining this, and this is just, well, if I'm thinking about some algebra that acts on the top space of some module and doesn't change the weight grading, right? I'm always living in the zero graded part, then L0 has to be commutative, right? L0 shouldn't be moving past any of these generators and picking up any extra factors on the way through. Otherwise, you'd be changing the grading in some way. That's maybe the easiest way of seeing such a thing. All right, so let's try a quick calculation. Now we're doing math live, so things are always possible to go wrong. But let's say I wanted to calculate in this Zhu algebra what the product of J0 and G plus 0 is. Well, I take my product from before, and now I have some expression like this. Now, thankfully, the binomial saves us really a lot of space. So here I can write something nice down. The first term that I'm going to have is the J0 term. So here I'm going to have J minus 1 acting on G plus's zero mode. whatever the representative of that is in my quotient. And then the next term along, I'm going to have J0 acting on G plus's zero mode, whatever the corresponding representative of that is. Now, the first term is very nice, right? The first term here, this is just going to be J minus 1 acting on G plus's zero mode is the same thing as the zero mode of the normally ordered product of a J and a G plus. And it turns out that that's fine for us to be something that we just carry around through the calculation. The next term is where things can maybe get a little bit more interesting. So here, what I need to do is I need to try and commute this thing past. So what do I mean by that? Well, J0 acting on G plus, I can imagine this, or I can rewrite this as the zero mode of J0 acting on G plus minus 2 because of my conformal grading on my algebra, acting on my vacuum vector, right? Here I have 1 standing in for my vacuum vector, and this is the corresponding zero mode. Now, if I can get J0 past to act on my vacuum, I know that J0 annihilates my vacuum vector. That's very good. So we can try and commute these things past. So here I'm going to have, and I'm going to write in purple brackets for commutation relations, I'm going to have the commutator of J0 and G plus minus 2 acting on 1, and take the corresponding zero mode of whatever this is. And this turns out to be very nice. This just gives us an overall plus sign. And here I have the representative of G minus 2 plus acting on 1's zero mode. And that is just what I'm calling G plus 0. Great. All right, so there's a sample calculation. This is telling us that, okay, this whole thing here, if I take this, go down here, this is equal to the zero mode of J G plus 0 plus G plus 0. Now, I still need to calculate a bunch of other relations amongst all of these things. For example, I need to calculate G plus multiplied by J. I need to do things the other way around. I can save some time. I've done that. Let me just quickly copy this so we can pop it on the next page because I know it's not there. All right, so there we have the remaining relations. So let me just drop that there. So the remaining relations become the following. So J0's commutator, again, I've written the commutators in purple because there's a lot of square brackets going around. Hopefully people can follow. Commutator of J with a G plus minus gives me plus minus whatever I had before. Then the only other thing that's left for me to calculate is what the commutator of a G plus and a G minus are, and that's a little bit complicated. We get kind of a mess. But the main reason to care about such a calculation is that this gives us a really concrete handle on the Joux algebra. And then what we can do is we have such a nice concrete presentation of this algebra. It's very straightforward for us to then go ahead and study Joux modules, right? But at the end of the day, what we want is we want the modules of this algebra, right? The reason for that is nicely encapsulated by Joux's original theorem, right? So that theorem is that there's a bijection between simple Joux modules, which I've written as M bar, and simple n-graded V modules M, right? So the idea of this correspondence is that if I have such a V module M, then the top space of that module is very naturally a Joux module, and correspondingly, if I have such a Joux module, then there exists some way of inducing that thing to a V module such that the top space is isomorphic to the thing that I started with, right? Now, of course, I mean, there's of course many experts in the audience. We know that there's been generalizations of this, and it's maybe the simple statement here isn't quite all that one can extract from the construction that Joux gave, but I think for the purposes of at least for this discussion, it's enough to state this particular version of the theorem and at least just say that I think what the physicist's approach offers is a very nice way of calculating concrete realizations of these algebras. All right, so if there are any questions, I think the next slide involves a bit of a change of tack. But the idea really, like the takeaway of all of this is that we have some nice way of calculating these algebras, and these algebras and their representation theory are very intimately linked to the representation theory of the vertex operator algebra itself. And I think it's fair to say much easier to deal with than VOA modules, right? Anyone who's spent time studying VOA modules knows that they are notoriously slippery. All right, great. Well, if that's the case, I'll forge on. That's a good way to be. Now I'm going to change speeds somewhat, right? So now what I really want to talk about are things called W algebras. And we'll link all of these things back together in a second. But at first, it's maybe going to come a little bit out of left field, especially for non-experts, right? So there's been a lot of recent focus in our community, as I'm sure people can tell just by the titles in the talks in this seminar series, right? On these things called W algebras, right? What is such a thing, right? As a quick reminder at this point, right? If I have some simple Lie algebra G and I take some nilpotent element inside of G, right, I have an affine VOA that I call VKG that corresponds to G in some way, and I can define a W algebra by something called quantum Hamiltonian reduction, and such a thing depends on a choice of simple Lie algebra G and choice of nilpotent element F, right? There's some cohomological procedure that I don't think we need to get into that defines for me some W algebra. This is some VOA. In this case, it's going to be enough just to think about the universal VOAs, right, that I get out of this nice construction. Now, we have a lot of structure, right? In type A in particular, the nilpotent elements that I can use, right, they're classified by Young to Blow, or partitions, if you want to think about it that way instead. And so each one of these Young to Blow, or partitions of N, will lead me to a non-isomorphic W algebra, right? So in the case of SL2, this is perhaps particularly nice, right? I can either take my trivial nilpotent element, which is just 0, and I perform Hamiltonian reduction and I get back the thing that I started with, or I can take the regular nilpotent element, which is just the usual F we think of inside of SL2, and what I get out is the universal Virasoro algebra. Right, if I upgrade this to SL3, then I have 3 possible W algebras. I have the trivial W algebra, which is my affine thing. I have the Beshadsky-Polyakov algebra, which we saw before. And at the bottom tier, right, if I take again my regular or my principal nilpotent element, I have Zamolodchikov's infamous, maybe famous W3 algebra. All right, now things, of course, can get a little bit more interesting. When the number of partitions is small, the Young to Blow are easy to stack on top of each other, right? If I let things get particularly hairy, maybe I look at something like SL6. I don't have enough space to draw in all of the boxes, but I have some sort of diagram of embeddings, which is probably the wrong word to use, but I have at least a diagram of partial orderings on my Young to Blow, which looks something like this. So at the top, again, I have my affine. At the bottom, I have my regular W algebra, which physicists would call W6, for example. And inside, I have this whole stack of W algebras of various kinds, all non-isomorphic to each other. And in principle, between some of these W algebras, it's possible for me to partially reduce, right? What do I mean by that? Well, quantum Hamiltonian reduction, as I've sort of pointed it out here, in the above, so it starts at the top of one of these diagrams and given a choice here, lands me somewhere inside, right? Maybe I start at the top and I land at BP. I start at the top, I land at W3. Maybe I start at the top and I land here, for example. But this idea is that I have some process that I can apply once. What's become very interesting, at least, is this idea that, oh, well, I mean, it's not necessarily a recent idea, that perhaps I can perform these types of reductions multiple times, right? So it might be possible to reduce, and it is possible to reduce from here to here and then from here to here, right? I can start with BP, perform some analog of quantum Hamiltonian reduction in that setting and end up with W3. Or maybe there's some path I can trace through this big, huge mess that means that I have some way of reducing, maybe like this, down through my structure. Okay, so this is sort of a very broad, very quick overview of quantum Hamiltonian reduction, at least as it applies in type A. What are we doing this for? Well, I want to maybe introduce one more thing, right? So attached to each affine W algebra that we've defined as above, right? At least if you believe there's some process that does this, we can associate something called a finite W algebra, right? So this was originally defined by Premet in full generality. I mean, I think the very first work on this it was very old work by Constant, who was looking purely at, I think, principal reduction. But Premet gave a very nice general definition of what's going on here. So what do I mean by a finite W algebra? That's a very good question, right? So the idea is that if I have some affine thing, well, there should be some corresponding finite thing. What I mean by finite isn't really finite, but it turns out the correct thing to think about is the universal enveloping algebra, right? So if I have some affine VOA, I can refer to its finite W algebra. In this case, this is the, I think about this thing here as being a trivial W algebra. This here is a trivial finite W algebra. I have some nice unital associative algebra, which is far less complicated than VKG. And now more generally, how I might want to define a finite W algebra is it's an invariant subspace of a quotient of U of G by some ideal that depends on F, right? So the actual definition, again, is complicated and a little bit ugly. But if I go far enough through, it turns out that if I take, for example, the universal enveloping algebra, and I do this finite W algebra corresponding to the regular element, what I get out is the center of my universal enveloping algebra. And sort of in between that, I have sort of some space between U of G and the center of G that I can reduce my way through. That's at least the game. And so I can denote this thing by UGF, right? So this is going to be my notation for the finite W algebra corresponding to G and F. I need a choice of both of those things. And again, this is some invariant subspace in a kind of complicated way that arises out of a quotient of U of G by some ideal that depends on my choice of F. All right. So the finite W algebra, it turns out, sees much of the structure of this game of quantum Hamiltonian reduction by paths, right? What do I mean by that? Was this is this conversation I was having about finding these funky paths through things. Right? The finite W algebra is in some sense able to detect a lot of this structure, right? So there's a very nice paper by Naoki Genra and Thibaut Juillard, which came out now nearly 2 years ago, which outlines a lot of when these what are called partial reductions or reduction by stages are possible, right? So there was some previous work that looked at some type A cases by Madsen and Ragusi from I think like the mid-90s, and what they see in that example mostly comes from the Poisson algebra point of view, sort of the classical version of a W algebra. But Naoki and Thibaut's paper does a very good job of cleaning things up and introducing some of the more modern combinatorics, right? And part of the benefit of this is there's like a significant body of work in the math literature on the reps and the structure of these finite W algebras. Now, I've sort of gone on for a long time about this seemingly different approach to things, or like wildly different topic. But these two things are linked, right? There's a very nice theorem by Katz and de Soleil from 2006, which says essentially the following statement, right? The Joux algebra of an affine W algebra, right? By this, I just mean one of my Hamiltonian reductions is isomorphic to a twist of the corresponding finite W algebra, where this twist is generated by what they call a Hamiltonian operator. In our case, there's going to be some automorphism that we can generate using L0. Okay, so this seems to be a very powerful statement, maybe a little bit out of left field, but it's telling us that, okay, by studying finite W algebras, we're also studying, in essence, the Joux algebra of my affine thing. So all of this work that we have in the math literature on the representation theory and the structure of these finite W algebras, we can essentially put to work on the Joux algebra side of things and on the rep theory of our affine algebras. Okay, so we can see this nicely in an example, right? We worked out, or I worked out, and we saw some together, this earlier example of Joux BP, right? So this was the algebra we had before. Now, this is a very nice older paper by De Boer and Chin from 92 that was the first paper to go through this process and give a concrete realization of what the finite W algebra is for SL3 if I take this subregular F. Right, so this is generated by 4 elements, an H, E, F, and a C, where C is central, and the other relations have this commutation relation here. So hopefully this is close enough these two expressions or two sets of expressions are close enough to each other for you to believe me when I say that there's only really a twist between these two things, right? And that's really the power of this whole picture, right? So these links have proven really powerful when we can calculate explicitly, right? So we have nice relations between things like Joux algebras and W algebras in the minimal and the principal cases, but we don't quite have enough structure of what's going on to see everything inside, right? So this is telling us in these complicated stacks of things, we know a lot about what happens very close to the top and what happens very close to the bottom. But as the rank grows in size, right, the inside of these diagrams gets really complicated. It's very difficult to see. Moreover, we certainly don't have enough structure to see some very interesting reductions, such as what Shigenori spoke about, I think, 2 or 3 weeks ago now. We have this sort of webs of W algebras. You have these reductions between SLNs of different N, right? And there's not quite enough there yet, or at least these tools here haven't been developed quite enough to see that side of the picture. Right, so this motivates trying to find some overarching structure where all of these things fit inside. And now finally, with sort of like 5 minutes left, we get to Yangians, right? Okay, so what is a Yangian? Yet another part of the picture, and unfortunately, an unfortunately ugly part of the picture, but nevertheless, we forge ahead. So let G be some simply laced Lie algebra, right? So I'm going to sort of shrink the space of G's that I care about, but that's where we have results for the Yangians. So what is the Yangian? So the Yangian is a unital associative C algebra that's generated by a certain family of generators, right? So this should be reminiscent of the Chevalier generators for your Lie algebra, but now I have sort of infinitely many of them, right? Here I allow each of these things to appear with some super index that's allowed to be any positive integer, right? And so I have I, which runs from 1 through rank G out of all of these, and it satisfies some set of relations. Now, I haven't written all the relations down. There are a lot of them. I'm not sure how much is to be gained by seeing them all. What I want to do was try and produce, first of all, some relations that should look pretty familiar, right? We have some set of relations in our Yangian that look very similar to the types of relations you expect to see on a Lie algebra. But then we have an additional set of relations which look much worse than you expect to see in sort of like the enveloping algebra for Lie algebra. For example, this is a relation here. So I have like the difference between commutators of H's and E's gives me some linear combination of H's and E's. And similarly, I have some relation like if I and J aren't neighboring each other, aren't equal to each other, then I can define some quantity like this. And I have something that looks like a Serre type relation, right? That's sort of reminiscent of that, but it's a little bit more complicated. I need to take some symmetrized sum over this whole mess. Nevertheless, so I have some unital associative algebra, albeit ugly. What can we do, right? Seems like a remarkable mess to understand. How do I sort of get a conceptual handle on such a thing? Well, this Yangian, at least in this presentation, and that's one of the other frustrations, there are many different ways of presenting a Yangian. This Yangian is a deformation, or at least you can think of it as a deformation of the enveloping algebra of like a semi-loop algebra. So if I take some G, I tensor it just by the positive polynomials, right? And not like loop in the usual affine sense. And then I can think of this as like a quantized deformation of this particular enveloping algebra. And indeed, I get an embedding, right? If I have some, if I want to find the enveloping algebra of my G, well, this embeds in the Yangian. And this embedding, right, the generators of this are given exactly by the generators that I would have in terms of E, H, and F, where I take any subscript, but I only take the superscript 1. Okay, how does this all relate back to my previous picture? What is my link? Well, to each young tableau lambda of size n, I can associate an n by n matrix that I'm going to call sigma lambda. The entries of this matrix are non-negative integers, and this thing's called a shift matrix. This shift matrix can be used to define something called a shifted Yangian. What the shift does is, depending on the entries of this matrix, I keep all of my EIs and all of my HIs, but I throw out some subset of my FIs, right? How many I throw out depends on my matrix. And this algebra gets some new algebra, right? This is some sub-algebra of what I started with. I've thrown out some generators. but it satisfies all the same relations, of course, keeping in mind the fact that I've effectively set some things to zero or thrown them out. Okay, so I have some nesting of subalgebras. Now, there's still one more step to this game. I need to introduce something called a truncated shifted Yangian that I'm going to call y bar. So this is now a quotient of my shifted Yangian by some polynomial ideal that appears in the H's, right? So I write down some polynomial in my H's. This generates a two-sided ideal. The polynomial that I get depends on lambda. What's fascinating, though, is that once I've done this huge process, what I actually have is I have an isomorphism between the finite W algebra that depends on lambda and the truncated shifted Yangian, right? So this was first observed in GLN by Ragusi and Sorba for only what are called rectangular partitions. This formalism was generalized by Brennan and Kleshchev in 2004 to all the Yangians related to GLN, and then there's been much more work after that, sort of restricting things to these ADE types. Now you can verify, you can take, for example, this lambda, you can fill it in appropriately according to their rules, you write down this matrix here, this is our shift matrix, and you can show that this truncated shifted Yangian reproduces this Debord-Chin algebra that I wrote down before. It's a little bit of work, but it's all there. Now, why go to this effort? Why they introduce this thing? Really, what we seem to see here is that this Yangian formalism collects together all of our finite W algebras in some nice holistic way. The trade-off of having them all packed into one structure together in some kind of nice way is that it's algebraically much more complex than what we started with, right? So we've traded in the fact that, well, these finite W algebras, they're quotients of UG, and if I change G, well, there's not really a nice way of nesting UGs inside of each other. Here, what I'm getting is a trade-off. Right? I can start to nest things inside of each other in a much nicer way, but the algebra I have to deal with is harder. Now, it raises a lot of new questions, right? How can I try to exploit this link for profit? Now, a lot is known about the finite dimensional irreps of these truncated shifted Yangians. Less is known for the infinite dimensional reps, right? So if you want to study something that isn't sort of rational W algebras, then the interest is really in understanding the infinite dimensional representations of these things. How much of the reduction by parts picture or combinatorics, right, this sort of pairing, when can I do these 2 or 3 stage reductions, can I see via Yangians, right? So this is kind of a, I mean, I don't know if it's fully open, but I think it's pretty evident that Thibault and Naoki have taken ideas from this space, particularly in their use of pyramids, but I don't know if this correspondence is completely made concrete yet. Something else I found very interesting is that not all truncated shifted Yangians are W algebras, right? So the construction of such a thing leads to a larger family. So all finite W algebras are truncated shifted Yangians, but the converse is not true. And so it leads to an interesting question of, okay, well, if I can define some bigger thing, and I have some way of thinking about this as the Jou algebra of some VOA, well, what VOA is that, right? How can I sort of join these dots together? And the last thing that sort of comes up in this is that these truncated shifted Yangians have a natural construction as algebras on the Coulomb branch of what are called BFN quiver gauge theories, right? So there's a lot of machinery here. This is something that I really don't understand all that well myself, but people like Ben Webster and Joel Kamnitzer and Sasha Braverman have been working on these types of ideas quite a lot with a number of their students, and there's a lot of literature out there. I at the moment, and I dare say may never, understand enough algebraic geometry to crack through exactly what they're saying, but I think there's a lot of very interesting ideas there that if we could translate them into a sort of a VOA picture, by bridging this a little bit better, I think would be really great for all involved. All right, so that's maybe where I want to leave it. Thank you for letting me go maybe 4 or 5 minutes over time, and thank you all for listening.
Thank you, Chris. Let's thank Chris, and let me stop the recording so we can start with some questions.